Right. Bismillahirrahmanirrahim. Just to recap back on what we did last lesson, basically we looked at why carboxylic acids in general, sorry, in general, carboxylic acids are more acidic than the phenols, alcohols, and even water, okay? Just like explaining the acidity of other functional groups, you need to look at the stability of the anions. Basically, if the anion is stable, it is more likely to be formed. I don't know why I'm losing my voice. So basically, more ions, more acidic, okay? Because more ions means you are favoring the ionization reaction, which is the forward reaction. And if you have a lots of H plus ions, you must also have a lot of anions. Okay, so the stability of the anions help you to explain the acidity of the different functional groups. Yesterday we saw that in carboxylic acid, there is a delocalized system in the COO minus part of the carboxylate ion. Basically, the p orbital of the pi bonds between the C double bond O overlaps with the orbital of the lone pair on the oxygen with the negative charge. Okay, so what happens during delocalization is the double bond is not fixed on the C double bond O. It is now being spread out throughout the COO minus. Okay, so that's why you will see some drawing that draws it as a dotted line. And also the negative charge is also not concentrated on the oxygen, but more like being spread out to the whole molecule. Okay, so that delocalized system helps explain why carboxylic acids are more acidic than the other functional groups. Okay, remember that there are two explanations that you can use. The first one, you can talk about the stability of the anion. The second one is you talk about how concentrated or how what's the opposite? I wouldn't call it diluted. How concentrated your charge is, because the more concentrated your charge is, the more it attracts your H plus, the reverse reaction happens, okay? The third one is the strength of the OH bond, okay? The general rule is that if you add electrons to the bond is stronger. If you remove electrons from the bond is weaker. Okay, so what's the relationship between the strength of the bond? Well, if the bond is weaker, the OH bond is weaker, that means you release more H plus, therefore more acidic. Okay. Right, today we're going to look at the strength of carboxylic acids, okay, just within the functional group. That means we're not looking at the other functional groups. The learning objective is to use the concept of electronegativity to explain chlorine substituted ethanoic acids, okay? So the strength of a carboxylic acid can be affected by the nature of the substituent group. Now, if you're wondering what a substituent group is, a group, an atom or a group of atoms that has been attached to one or more atoms in the carboxylic acids. Okay, so for example, the hydrogen is being replaced by chlorine. So chlorine in this case is a substituent atom. So you can have two types of group that have opposite effect to each other: electron donating group and the electron withdrawing group. Okay, this is especially useful when you want to talk about the stability of the anion. Okay. First, we look at the electron donating group. In general, electron donating group is said to decrease the acidity of the carboxylic acids. Okay, one of the common examples that you have used as an electron donating group is the alkyl group. Okay, methyl, propyl, butyl, ethyl, and etc. So if you want to compare the acidity between a propanoic acid, okay, here is a propanoate ion, okay. So if you want to compare the acidity of the propanoic acid and the ethanoic acid, okay, you cannot talk about the delocalization. You can't say that one has a better delocalization than the other. No, no such thing, okay? So that means we're not looking at this part of the molecule. We don't talk about the COO minus since both of them have that same group, okay, or that same delocalized system. That means we want to focus on the substituent, whatever is attached to it, okay? Now this is an ethanoate ion on the left, propanoate ion. How do I know that? Because I count the number of carbon, okay? Do not miss out the carbon on the COO or the COOH part of the molecule, okay? So this is an ethanoate ion, again, because I have 2 carbons, okay? Now, these 2 acids, propanoic acid and ethanoic acid, have different acidity, okay? It turns out that ethanoic acid is more acidic than propanoic acid, okay? The reason for that, both of them contains alkyl group. Both of them have the same electron donating effect. Well, the effect is the same, but sorry, they're both electron donating, but the effect is not quite the same, okay? One has a better effect at electron donating than the other, okay? So if you look at the propanoate, remember that this ion is a negative ion. Now, propanoate, it contains an ethyl group. So ethyl group, the bigger the alkyl group is, the more effective it is at electron donating. Okay, so if I want to compare the electron donating effect of an ethyl group towards the COO minus and a methyl group towards the COO minus, obviously the ethyl group would be better at donating electron. Okay, so I'll draw 2 arrows showing you the relative effectiveness, who is better or who is donating more electron density. In this case, ethyl donates more and a methyl donates less. Okay, now the 2 arrows and the 1 arrow is just showing you the amount of electron density being donated. Okay, there is no unit or whatsoever, it's just the relative amount, right? Now, if you think about it, you are a negative person, you receive electronegativity from a friend, whatever, okay? Obviously, both of these anions are unstable, okay? Both of them are unstable, but one is more unstable than the other, okay? So you can see here, ethyl group is a much bigger alkyl group compared to methyl, so it donates more electron density, okay? You're already negative, you're receiving more and more negativity, so you become more and more unstable, okay? So here we say that the propanoate ion is more unstable than ethanoate ion. Propanoate ion is more unstable than ethanoate ion, okay? Both of them are unstable. So the idea is the more stable ions will be more likely to be formed, therefore more acidic. So that's why ethanoic acid is more acidic than propanoic acid, okay? I hope that explains. The size of the alkyl group can actually determine the acidity. The bigger the alkyl group, the more it donates electron density, the more negativity it donates to a negative person, and therefore makes it unstable. Unstable, less likely to be formed, less ionization, therefore less acidic. Okay, I hope you got that. Right, so this is just, again, the same thing, comparing a methanoic acid, an ethanoic acid, and a propanoic acid. And from the numbers, okay, you should know from the numbers itself, pKa is the same as pH, okay? The smaller the number, the more acidic it is. So this is the most acidic. Methanoic acid is the most acidic, with the propanoic acid being the least acidic. Okay, now if you remember, if you just imagine that these are the ethanoate ions, okay, maybe I'll just draw it so as to not confuse you. I'll just draw methanoic and C2H5. Okay, so if you look at the methanoate ion, hydrogen, oops, what am I doing? Hydrogen is neither electron donating nor withdrawing. Okay, so there's no electron donating effect there, but you know, it's still a negative. So there is some sort of stabilization in a methanoate ion. As compared to propanoic acid, you have a C2H5, which is very electron donating. Okay, so the ethanoate ion, the propanoate ion is less stable than the methanoate ion. Okay, so less stable, less likely to be formed. Okay, less ionization, therefore less acidic. Okay. Nothing much to talk about here, so I will just move on. I hope you can understand that. Now we move on to the next type of group, which is electron withdrawing group. Okay, so electron withdrawing group has the opposite effect to electron donating group. Okay, so in this case, usually the electron withdrawing groups are the electronegative elements. Okay, now we know that fluorine, oxygen, nitrogen is the highly electronegative elements, but don't forget chlorine is also an electronegative element. So how does chlorine withdraw electron density from the COO minus? Basically through a chain reaction. Okay, so chlorine, this chlorine will pull the electron density from the COO minus like that. Okay, so chlorine first pulled the electron density of the carbon-chlorine bond and then the carbon-carbon bond. Okay, so if you notice, the arrow is also the opposite. Okay, for electron donating, the arrow is showing that the electron density is going into the COO minus. For chlorine, the electron density is going away from the COO minus. Okay, now if you're a negative person and you have a friend who takes away your negativity, you become a little bit more stable. Okay, now you do not lose that negative charge. Okay, I do not want students to think like, oh, chlorine has removed my electron density, so my negative charge is gone. You still have that negative charge. Okay, removing electron density just means that you are pulling the electron cloud. You're not completely taking the electrons away, hence the negative charge. Okay, so you will still have negative charge. It doesn't change. It's just that now you have less negativity on your shoulder. Okay, like you know, when you have a friend coming who approaches you and then try to talk to you, try to lessen your negativity, you now feel better, but you don't automatically lose all the negativity, right? You still have some sort of negativity inside of you. It's just that it's less now and you become a little bit more stable. Okay, so electronegative chlorine atoms withdraw electron density. So please understand that electron density is just like you're removing a region, okay, a region of the electron cloud, right? You're not really taking away the electrons. Yeah? So you withdraw electron density from the COO minus ion, which is this part, because that's the part where you have the negative charge. Okay, so if you take away negativity from a negative ion, this makes the ion becomes more stable. So this is the opposite effect to electron donating group. Okay, so chloroethanoic acid is more acidic than ethanoic acid. So if I just draw the ion of an ethanoic acid, which is the ethanoate ion. Okay, I'll just draw it like that, right? These two things are the same if you haven't noticed, okay? The way that I have drawn my COO minus, whether I draw it as a dotted line or a double single line with a negative charge on the oxygen, it's the same. Okay, it's just that this part is showing you the delocalized system clearly. Here it doesn't show any delocalization. Okay, if the question doesn't ask you to show the delocalization, then just draw it normally like this. Okay, right. So we're comparing the chloroethanoate ion and the ethanoate ion. Okay, now naming, I hope you can see that this ion is called a chloroethanoate ion because there are 2 carbons and there's 1 chlorine. Okay, so the acid will be chloroethanoic acid. Right, so if you compare these two, there's a chlorine that pulls away, that removes some of the negativity or remove the electron density in the chloroethanoate ion. But in the ethanoate ion, which is the drawing at the bottom, you have an alkyl group that donates negativity. Okay, so you can see these two have the very opposite effect to each other. Top anion is more stable and the bottom is less stable. Okay, also don't get confused with the arrow. Okay, I hope that arrow is easy to understand, but I've had students in the past who cannot see like what is the arrow doing. Okay, basically the arrow is just showing you the direction of the electron density. Okay, you push electron density into COO minus and you withdraw or you pull away the electron density from the COO minus. Okay, let's have a look at this 3 different chloroethanoic acids. We have 3Cl here, trichloroethanoic acid. In the middle diagram, it's the dichloroethanoic acid, and the very one on the far right is the chloroethanoic acid. Okay. Before we look at the structure, we can already look at the pKa value. The smaller the pKa value, the more acidic it is. So in this case, trichloro is the most acidic, and the chloroethanoic acid is the least acidic. Okay, reason for that? I hope you can see that there are 3 groups that can withdraw your negativity. Okay, so a bigger pulling effect on your negativity. I was using this example with the other blob, but I don't know if it applies. Basically, it's like you're a negative person and then you have 3 friends or 3 people to comfort you. So to take away your negativity. But then I just realized that maybe, you know, some people don't like having many friends to comfort you. You prefer 1 person. Okay, so I will not use that example. It'd be like that sometimes. So yeah, basically, just look at it as being a more electron withdrawing group to remove more electron density from you. Therefore, you become most stable. Okay, so this ion, well, it's not an ion, but when it forms an ion, actually, I will not call it most stable because otherwise, yeah. Okay, so the trichloroethanoate ion will be the most stable, and the least stable because you only have 1 chlorine atom to remove your negativity. Okay, so I hope that is self-explanatory. The greater the electron withdrawing effect, the stronger the acid. Okay, that's why you have 3 chlorine that is an electron withdrawing atom. Therefore, the more stable your anion is, the more acidic it is. Okay. Next one, we want to look at the different halogens. Okay. Notice that everything else is the same. You have the same number of carbon in each of these molecules. There are 2 carbon atoms in each of the molecules, and the only thing that's different is the halogen. So, well, you should be looking at the electronegativity strength. Okay, and we know that fluorine is the most electronegative element. Therefore, if I draw the arrow again to show you the the effect of withdrawing electron density, fluorine will be the strongest. So I will draw 4 arrow, and then iodine being the weakest at pulling the electron density away from the COO minus. Okay, so that's why you will see the pKa value. The one with the fluoroethanoic acid is the most acidic. Okay, notice that they are only changing one factor at a time, right? The first one just now, this one, yeah, this one is the number of electron withdrawing groups. Okay, you have 3 versus 2 versus 1. Here is the type or the strength of electronegativity, okay, which is fluorine being the most electronegative and iodine being the least electronegative. Okay, the last one is the distance, right? If I number them, okay, this will be carbon 1, carbon 2, carbon 3. Okay, don't forget to include your carbon of your COOH as number 1. Okay, students tend to forget that. Carbon 1, 2, 3, 4. So you can see that on the molecule on the left, your chlorine sits on the 3rd carbon. On the molecule on the right, your chlorine sits on the 4th carbon. Obviously, chlorine sitting on the 3rd carbon is much closer to the COO minus, okay, compared to chlorine on carbon number 4, which is further. Okay, so the effect of withdrawing electron is stronger when you are closer to the COO minus. Again, I don't see, any difficulty in understanding that. Okay, so as the distance of the electron withdrawing group increases, the effect on acidity decreases. Okay, so basically your chlorine is much further away, so it is not as effective at withdrawing electron density from the anion. Okay, so closer to the CO minus, the more effective it is, the more electron density you can remove. Okay, so you can see that the chlorine that sits on the 3rd carbon is more acidic compared to the chlorine that sits on the 4th carbon, which is less acidic. Okay, right. The next one, this one you can see, the closer the chlorine is to the COOH group, the more acidic it is. Okay, and then the chlorine 1, 2, 3, 4, furthest away from the COOH is the least acidic, because the electron withdrawing effect is the weakest. Okay, hold on, let's resume. Right, so I hope this is clear. You don't have this in your notes, but it's exactly the same as what you have in your notes. Okay, it's just that it is showing you clearly the distance or the location of the chlorine and the distance away from the COO minus. Okay, right. Okay, so with the other block, we stop at this slide, which is the reactions of the carboxylic acids. Okay, nothing much. Okay, nothing new here, because carboxylic acids act like an acid, therefore it can react with metal, alkali, and carbonate. Okay, so when acids react with metal, you will get salt and hydrogen. The salt is, again, I don't see why it would be something new for you. Basically, if it's an ethanoic acid, the salt will be an ethanoate ion, sodium ethanoate, potassium ethanoate, and etc. If your acid is a propanoic acid, your salt will be a sodium propanoate. Okay, so nothing fancy or nothing new there. So the box here, it says that the effervescence caused by the production of CO2 can be used as a functional group test for carboxylic acids. Now, for a reaction in organic chemistry, whenever you can see observation, whether it's gas being produced, you can test for the gas, or any color change, this reaction can be used to use as an identification test. Okay, so that means you can test whether there is a presence of a certain functional groups, like bromine. Okay, when bromine go from brown to colorless, or when bromine is decolorized, okay, that means a reaction has happened. Okay, so please remember, whenever you have a reaction that has an observation in your organic chemistry, use that as an identification, okay, a test to identify the functional group. Okay, for example, here, if you look at the reaction of carboxylic acid and carbonate, so you want to differentiate a carboxylic acid and an alcohol, okay? Only carboxylic acid can react with sodium carbonate, okay? So you will see carbon dioxide being produced. Alcohol will not react with sodium carbonate, okay? So this reaction can be used as a test to identify or distinguish carboxylic acid. Okay, so this is one of the few questions that were asked in your exercise. I haven't looked at your answers yet, at least not for exercise 17.1. Basically, they always ask you what test can be used to distinguish this certain functional group. Okay, so the idea is you choose one test that is positive for one functional group, but negative for the other functional group. So here an example is sodium carbonate. If you want to differentiate between alcohol versus carboxylic acids, you can use sodium carbonate, because sodium carbonate will only give a positive result with carboxylic acids. That is to say, only carboxylic acids can react with sodium carbonate. With alcohol, no reaction will occur. You will not see carbon dioxide gas being produced. Okay? Right. Now we have 9 minutes left. I will not start on this next learning objective, but I just want to recall back on your AS syllabus. Okay, so for AS syllabus, when you oxidize primary alcohol, okay, first I'm going to show the square bracket O start. Eric, start. Oh, recording. Thank you. Never mind, we're almost done anyway. So thank you, I just saw your text. When we oxidize primary alcohol, first it goes into an aldehyde, okay? And then it goes to carboxylic acid. Okay, so this is what we learned from AS. Now in A2, okay, in AS we said carboxylic acid can no longer be oxidized further. Okay, in A2 there are two types of carboxylic acids that can be oxidized further. Okay, so these two acids are methanoic acid and diethanoic acid. Okay, so that's something that is contradictory to your AS, to the things that you learned in AS. Carboxylic acids can be oxidized further, but only for certain. Well, for your syllabus, you only have to learn about two, which is the methanoic acid and the diethanoic acids. Okay, right, so that is all for today. I don't remember how much I did not record.